Okay, so now we know how to solve the engine replacement model, and we want to move on to figure out how to structurally estimate the engine replacement model and models in that class. And I'm going to do that first, and then we'll talk about some of the empirical results that came out of the paper, the engine replacement paper from 1987 by John Rust. Okay, so we estimate this model with maximum likelihood. So in order to estimate the model with maximum likelihood, we need a likelihood function. Okay. Now, we talked about the assumptions in the previous lecture. One of them was that the error terms, the epsilons in the model, was conditionally independent on the explanatory variables. Okay. That actually simplifies the whole likelihood function a whole lot, because the fact that the transition density factors in this particular way also makes it possible to write the choice probability or the likelihood function as a product of the choice probabilities P, the conditional choice probability, is conditional on X, and then the Mile-Rich process in this case, or the state variable process more generally. Okay. So we get really a likelihood contribution from this time period T1, conditional on the lagged values of the decisions and the states. Or you can leave the whole thing on it. So this likelihood function depends on two objects. Well, the capital P here, the conditional choice probabilities, and how did we compute that? Well, that was what all the first part of lecture 12 was about. How to derive the choice probabilities, how to find the fixed point, and how to express in an expected value function space. So if you're not up to speed with how to calculate that, I refer you to the first part of the lecture. Okay, but the key thing is we need to solve a dynamic program every time we evaluate the likelihood function. You see, it's here, the choice probability, and the choice probability also requires solving the dynamic program. It's going to be a little bit more transparent on the next slide. Okay, so we will also have to estimate the parameters in the transition density, and we can actually do that completely independent of the choice model. Okay, so we have data on the Mile-Rich, or the state variable process in this case, and with data on replacements, the decisions. Okay. So we could actually estimate theta 3 in a first step, irrespectively of the remaining parameters of the model. Now, this is something that is feasible because of the conditional independence assumptions. For instance, there's none of the parameters that index a utility function, the remaining parameters inside theta that affects the choice probabilities. There are none of these parameters that are entering in indexing the transition density. Okay. So in that sense, we can estimate it in a first step. Okay, we can do it either non-parametrically, or we can specify a parametric model for the transition density. What we did was we discretized the state space, and we parametrized how many the probabilities for moving up a certain number of grid points. Okay, so we did that, kind of a little bit non-parametrically. Okay, but still putting some structure on that these transition probabilities would be independent on the current state. So we're imposing some structure there, estimate parameters. Anyway, this can be done in a first step, and then you really have like a three-step procedure where we first estimate these first step parameters, and then you can put them into the transition density here, and then maximize the likelihood function only with respect to theta, the remaining parameters inside theta, keeping these first step parameters fixed. Okay. Now, think of that as giving really good starting values of theta 3. And then you could, in the third step, estimate the whole thing jointly, which would be the most efficient thing you could do. Okay. So these are like small, nice tricks you can do. If you can estimate a large share of the parameters in the first step without solving the model, well, you really want to do that. And even if you want to do a joint estimation where you impose any of these cross-equational restrictions that will be, or that improves efficiency, then you have a good opportunity to really get good starting values by doing this in several steps. Okay. Well, you'll try that out in the exercises where we'll replicate the results of Harris-Zucker's engine replacement model, published in Nonparametric in 1987. Okay, so a little bit more colorful slide. I'm going to repeat myself again, but I think this is something that we really need to have in place and be formal about and be precise about. Okay, so um, so here I've highlighted in red what is the parameters and I've highlighted in blue that EV is something special. It's special because it's really a function that's implicit function of the structural parameters. Okay, a solution to the dynamic programming model that you need to find with the fixed point algorithm. Okay, so what we have here is we start with data on replacements or data on the discrete decisions, DIT, and data on the state variables. In this case, mileage since last replacement for each bus I or each cross-sectional unit I at each time period. Now, really, to estimate this model, we don't really need full long length panel data here. But we do need two successive periods of data in order to figure out what the changes in the state variables are. Otherwise, we can't estimate the state transition process. Anyway, so with this data, we need to calculate the likelihood function, evaluate the likelihood function, which is essentially a function of the parameters. We want to maximize that with respect to the parameters. Okay, the likelihood function, well, that's the sum over all the buses or the cross-sectional units of the likelihood contribution. And now here we've taken the logs, and now we basically sum all the likelihood contribution for the different time periods. The log likelihood contribution for the first part refers to the choice log of the choice probability at the chosen alternative given the observed value of the state variable x or mileage. Okay, the second part is a log likelihood contribution associated with the mileage process, which is a much simpler part. I'm going to focus on this one here. As I outlined in the last lecture, these choice probabilities are multinomial logistic. It's just evaluating the logit formula. But there's a tricky thing here. There is the expected value function enters into the choice probabilities, which means in order to actually calculate the likelihood function, you need to solve the expected value function. Okay, how do you find that? Well, we don't have any closed form solution for the expected value. We need to solve a dynamic program. This is what you do by solving this functional equation down here. You could do successive approximations, as you've tried many times, where you just guess on an initial value of the expected value function. And since it's a contraction mapping, you can start from anywhere, and then you just iterate until that converges, and then the contraction mapping ensures that you're going to have a unique fixed point and you got your solution. Now, then once you have that, well, you have the choice probabilities, then you have your likelihood contribution. Now, all that machinery is just for a single evaluation of the likelihood function. But in order to find the structural parameters, you need to maximize the likelihood function. So you need to search over the parameter space with some hill climbing algorithm, like Newton-Raphson or BHHH or BGFS or whatever you have in your toolbox. Okay. Many of these methods are gradient based. Okay, so what it does is that it calculates the direction you want to go based in the parameter space based on the derivatives of the likelihood function with respect to the structural parameters. So if you want to be able to use gradient-based methods, it's utterly important that what you're differentiating is actually differentiable, that it's a smooth function. And this is one of the key benefits that you get from having the RD extreme value distribution. You get the choice probabilities being in closed form, logit formulas as smooth functions, and the max operator is completely gone from the Bellman equation. It's smoothed out and replaced by the log sum or the smooth max operator. So this means that everything here is smooth in theta, and we can calculate derivatives. It may be a little bit complicated to calculate derivatives because essentially the expected value function is an implicit function of the parameters. So you need to use implicit function theorem and calculate the Frechet derivative of the Bellman operator and whatnot. So this is, it's not super crazy complicated. It can be done, and this is something I'm going to talk about in the next lecture, where we compare the nested fixed point algorithm with the mathematical programming with equilibrium constraints, or MPAC. And the reason why I'm bringing it up there is because we are calculating these Fauché derivatives also to do the MPAC, so we can save a little bit on the time of going through the same stuff. Okay, so I'm going to defer some of the details on how you differentiate and how you actually maximize the likelihood function until next time. Okay, but these are the equations, and there is in the exercises code to implement all this. So I really highly recommend that you sit down with your computer and try to see equation to equation, from code to equation, and try to see if you can make the link. And otherwise, Malene, she will help you. Okay, so this is, I pretty much already said what the nested fixed point algorithm is, but let's just, really, zoom out a little bit and describe the overall picture here. It's really a nested algorithm in the sense that there is an outer algorithm that searches over the parameter space, okay? And then there's an inner algorithm nested inside the hill climbing algorithm, where you repeatedly compute the fixed point or the expected value function. Okay, so every time you vary theta, well, you need to find a new fixed point. Okay. One of the things we highlight here, compared to MPIC that we'll talk about next time, is that this is actually an unconstrained optimization problem, because the likelihood function, every time it's evaluated, we calculate EV at the present set of parameters. So it's imposing that constraint directly. It's imposing that the Bellman equation is holding. Okay. So the likelihood function here is maximized with respect to theta. You can do that by, very many different quasi-Newton type algorithms, because everything is smooth and differentiable, like BHHH or BFGS or a combination. And it's particularly the BHHH, or by Bernd, Hall, and Hausman, that algorithm that utilizes the information identity for maximum likelihood to make an Hessian approximation by the outer product of the gradients, really saves computer time. So if you don't know BHHH, you should find out how to implement that, because that's really a killer when you're estimating models with maximum likelihood. I'm going to say a few words about BHHH maybe in the next lecture too. Okay, so, well, each evaluation really requires a solution of EV, so we need to think about how to do that. We all know how to do a successive approximation. I kind of alluded to it in the previous slide. You start with a guess, you evaluate the Bellman operator, the output, you put it right back, and then you do the VFI, okay, the value function iterations. But you can also think of the Bellman equation as a set of nonlinear equations, or that you need to find the solution to. And what do we use to find solutions to nonlinear equations? We use Newton's method. And next time, I'm going to give you the details on how to do that, okay? Because it's really a powerful algorithm. It turns out that the successive approximation algorithm really slows down, especially when the discount factor is very close to 1. Whereas Newton-Kotorovich iterations is not linear convergent, it's quadratic convergent. So as you get closer and closer to the maximum, to the solution of the equation, you will converge faster and very faster, and errors will just, decrease quadratically. Okay, so how do you do this? And here's a little bit of simplified Python code taken out of the notebooks that are available for the exercises. I just wanted to just to point as an example to how we would implement this. Now, the likelihood function, or the log likelihood function here, takes the input value of theta. This is what we're varying. So when you're maximizing this likelihood function, you're varying the thetas in order to maximize what is coming out, namely the log of the likelihood. Well, so this is actually a vector of log likelihoods, and we usually work with minimization routines, so you would need to take the average of the mean, the average of the negative value of the log likelihoods, or the average of the sum, or something like that. But the reason why I return the vector here is because then it's very easy to calculate numerical derivatives of that vector, and then you got your score vector, which you need for calculating the outer product of the gradient. well, I'm kind of going a little bit of a tangent now, so let's go back inside. Okay, but the bottom line is something with the log likelihood is coming out, something with parameters are coming in. I'm putting in a bunch of, like, the data is coming in too, and then there's a model parameter structure that holds the information about, you know, what the potential parameters actually are, and the grids and so on. And then p names is really what are the the names of the parameters we want to estimate. Okay, and then there are some auxiliary parameters and the index of the explanatory variables, or the state variables, where that's in. Okay, so the first part of the code is really just unpacking, parsing theta into these model parameters, and then from the model parameters you can get the cost function evaluated over the grid. Okay. So this is really the cost function. As you can see here, we work with a linear cost function. So there's the parameter c here we are actually trying to estimate. This corresponds to theta 1, and the slide deck, and then multiply with a grid starting from 0 and all the way up to 450,000 miles, or you know, so that's really just a grid, and depending on how you initialize the algorithm, there can be as many grid points as you want, or you can calculate. But here, usually we work with 90 or 175 grid points as is done in the paper. But that's a setting that you set outside the likelihood function. And then we solve the model, and that's a key thing. When, like we had on the slide here, you would have to solve the model, meaning finding the expected value and finding the choice probabilities for every time you evaluate the likelihood function. And now we're evaluating the likelihood function. Okay, so we need to solve the model. This is what's going on here in these lines. Okay, so the first thing is we have some separate code that implement the Bellman operator. And then you can call it in two different ways depending on what it should output, and that's why we have two different anonymous functions here, and that's put into some general software we've written to use this Poli algorithm that combines successive approximations with Newton-Kantorovich iterations. Okay. In the exercises, you really get deep into the code and figure out how to code those Newton-Kantorovich iterations and what the string, when you should go from one algorithm to the other, and actually what every single line, I really encourage you to go through that. Okay, so having solved the model, well, then we can evaluate the likelihood, which is essentially, the likelihood, vector likelihood contribution from a standard binary choice model. So pk here, that's the output from the model, that's the probability of keeping, k for keep. Okay, and so we evaluate those choice probabilities are from the solutions are evaluated on the grid, and then what we do is we take the index that the data corresponds to. So if it's observed for a particular observation that you're in like the 5th element, well, then you will have the number 5 here, or probably 0, because Python has base 0 indexing. Okay, and then that's multiplied with an indicator for keeping the engine, and data d is an indicator for replacement, so that's 1 minus d. Okay, and then you have 1 minus pk, which is the probability of replacement, that is not keeping, times an indicator for replacement. Yeah, sorry for the confusion here. That's just, it doesn't matter, right? Compute doesn't care, but, maybe we should write some more pretty code. Anyway, so once you have done that, you have the first part of the likelihood. Let me just point out what we just calculated. This is this part of the likelihood. Now, the second part of the likelihood is fairly easy, straightforward, and what you can see here is that it doesn't depend, if you look carefully, it doesn't depend on anything that's coming out of this routine here. Okay? It's not depending on anything that's coming out of that routine here. So you don't need to solve the model. That's what that means. Okay, so you can essentially do that, and you can actually have done that in the first step, and we do so, and it turns out the maximum likelihood estimator in this case is really just a frequency estimator, the number of times or the fraction of times that a bus is in a certain is in a certain cell in the Merkle transition matrix. That's the maximum likelihood estimator. This. Okay, and then having done that, we just return the log likelihood, vector log likelihood contributions, and then you can average those, take the negative value, and minimize that objective function. So that's all about the Python implementation of the log likelihood function, and of course you could also go into details of how the Bellman equation is implemented and so on, and that you'll be able to see in the notebook. So I'm not gonna go carefully through the notebooks, but I can show you here that they exist. Okay. Oh, close, close, close. Don't allow close. Okay. So here we read in some of the modules. There's a module we really try to make things modular here, right? So that's a whole module that's specific to the model, like utility. What is the functional form of the utility function? What the Bellman equation look like? How do you calculate aggregate demand, and so on? All the things that are specific to the model of Harris-Zucker. Then there's a class called Solve, which is all about how you solve dynamic programming models, and we try to write that as generic as possible, so you can come with any Bellman equation and put it into Solve, and then solve it. Okay, and then estimate NFXP. Well, that's implementing the estimator and writing up the likelihood functions, so on, and maximizing likelihood functions, producing estimates, stuff like that. Okay, so you should look through the code eventually when you get to the exercises. Okay, so here you can run all this stuff. I just want to show you just one thing here. It is that if you use this code, you can actually replicate the results from the paper. So I should run this, and then you get this output here, and you will find that in the slide deck too. Okay, let's go back to the slides. Let's go back to the slides. Okay. So here's the output that you get if you run that notebook. Okay, so Harris-Zucker, what is he doing? Right? He's maintaining buses and figuring out whether or not you should replace buses. So the data consists of his maintenance record of 162 buses. And his monthly observations of mileage for each bus, including the odometer reading. Okay. And whether there was any maintenance going on, whether there was just routine periodic maintenance like brake adjustments, replacement or repair time of failure, or major overhaul or replacement on the engine. And what John Rust is focusing on is on the third category. So it's really a binary indicator. Either there's a replacement or there's not. Okay, and we have data on replacement and data on mileage. Here's just a explorative analysis of those data. So we can estimate the nonparametric hazard, which is essentially just grouping the data into bins of the mileage bins, and then calculate the fraction of each observation in each bin. That gives a very jittery curve, as you can see. So one of the problems here is that there's not enough data for each particular value of x to do a very flexible, or at least such a flexible nonparametric hazard. I mean, you may want to have to do a little bit of smoothing, or maybe estimate a more parametric model. And this is the business we are in, right? So one thing you could do is just assume beta is equal to 0 and then run a binary logit with of replacement on mileage. Okay, if you do that, you get this fit here. Okay, if you structurally estimate the dynamic programming model with beta equal to 0, well, then you get this fit. Okay, get this fit. Okay, and that's what we're gonna do. Remember last time that you had to specify the utility function. Inside the utility function, there was this binary, there was this cost function, this operating cost. That's a function of mileage. Okay. So if you incur normal mileage, you would just pay the cost, or Harris-Zucker would pay the cost of maintaining the engine within a month and on operating that engine as a function of mileage. If you replace, well, you have to pay the replacement cost, and then it regenerates to 0. So how do you specify that cost function? We just said it was a function of x indexed by some parameters theta 3. And what Rust is doing is he's trying out very many different specifications of this replacement of this cost function. Okay, it's looking at cubic, quadratic, linear, square root, power, hyperbolic, and they have varying number of parameters. You can estimate all these models, and you can also estimate them on different data sets. So there's different groups of buses, bus 1, 2, 3, and bus 4, and then a combined group of buses. And here, what you see below here is essentially the partial likelihoods associated with each of those specifications. And one is for beta equal to 0, and one for beta equal to 0.999. And you can see it's actually pretty hard to reject that, just looking at these partial likelihoods, that they are essentially identical. So, but this is because it's estimated with a two-step approach here. So you may get a little bit more power by estimating these two equations jointly and then learning about the specification. Anyway, so we will look for the one with the lowest likelihoods, probably the square root. I think we continue with the linear function, and then we'll try to look at the structural estimates. Okay, so here they are. And the structural estimates here, they are for a fixed point dimension at n equal to 90, so 90 grid points of x. Okay, this corresponds roughly to a cell of mileage intervals. At mileage interval would be 0 to 5,000. The first cell. Next would be 5,000 to 10,000. So the length of those intervals is going to be 5,000. And then since the 90 grid points all the way up to 450,000 miles. Okay. Now you also consider a case with more grid points, 175. And you can see some of the parameters are actually sensitive to whether you choose one or the other. Some of the parameters are not really that sensitive. Okay. So let me just explain briefly. These are the parameters that you get from estimating the static model. And one of the things to notice here is so the parameters of interest here is really the replacement cost parameter. Okay, so there's a higher replacement cost in this area, but if you compare it to the size of the marginal cost, is not that high compared over here. Anyway, there's certainly differences. So this is the slope parameter in the cost function. So there's only one parameter in theta 1. And then the theta 3 and 0 and theta 3, 1, these are parameters that index the mileage process. Okay. So this is, for instance, the probability of staying just in the same state, and this is the probability of moving up one state. Now, the first thing to look at is actually those, because if you increase the fineness of the grid from 90 to 175, there's going to be more of those parameters. Recall last time we looked at these parameter estimates, or the transition matrices, with these banded matrices with numbers of the diagonal, and then suddenly they become zeros because you get out in areas where there's just no buses are driving that far. But now when you slice the intervals more, there's going to be more non-zero elements because you now start to distribute out those parameters. Okay, so that's why when you increase to 175, there's not only a theta 3.1 and theta 3.2, there's also a theta 3.3. Okay, so the number of parameters has actually increased. And so they mean something different because it's a probability of staying in a smaller cell in the case of 175 compared to where that probability is 0.44, and over here the probability of staying in that first state is smaller because the interval is essentially bigger. Anyway, I'm not sure I fully understand that, but it's certainly different. Okay. Okay, I'm totally missing it. I'm looking at the wrong one. Okay, this was super counterintuitive. So it's 10% of not moving when they're small. That makes a lot more sense, okay? And then it's 30% when their interval is big, okay? So it's not moving out of that first interval. And then moving one interval up, you have 0.68 or around 70%, whereas it's 44 in the more fine grade. Anyway, so these are the parameters that you can estimate in the first step. Okay, here they are actually estimated jointly with the remaining parameters. Another thing to notice is that the parameter that indexes the cost function, like the slope, really this parameter here multiplied with x, well, that's just much smaller in the case where we have a finer grid. Well, but that's because now this is almost twice as big, this grid, right? So in order to really get up to the area where you have a higher mileage, then you need to jump to almost two intervals. Okay, so they're roughly like twice the size when the intervals is twice as big. Okay, of course, this makes these two graphs tables a little bit hard to compare, and I think the key thing what he wanted to do was to figure out, is this approximation of the model fine enough? Okay. One thing that's not affected so much by this is the replacement cost parameter, and you see it's roughly the same across all specifications. Okay. So another thing I want to highlight here about those estimates is the difference between the static model, those estimates that you get down here, and the dynamic model, those estimates that you get up here. Okay. This dynamic model has much higher replacement cost compared to the remaining parameters. Okay, and you know, remember that the parameters here are only identified up to scale, so it makes sense to actually just divide them to each other to get the scale out. Okay. And you can say replacement costs appear to be high compared to the slope of the cost function. Okay. Why is that? I mean, we are taking the same a static version and a dynamic model version of the same model to the same data. Okay, Hirasaker, he's replacing as he is in the data. There's a limit number. There's a certain number of replacements as a function of the mileage. Now, if Hirasaker is forward-looking, he is willing to incur a higher replacement cost, right? Because he knows he's making an investment, and he knows that tomorrow he is getting the benefit of that investment by having lower maintenance cost, maintenance and operating cost, lower cost per period cost. Okay? So that's why he's willing to incur higher cost. Okay, so if you're wrongly estimating a dynamic model in a case, or in a static model in a case where he's really behaving dynamically, then you're gonna severely underestimate the parameters that indexes the replacement cost, the cost of doing an investment. Because in order to rationalize why he's doing all those investments, if you're not forward-looking, well, those costs must have been very low. Okay? And this is why a static model is severely under-predicting what the cost of replacement is. Okay, I think that's enough about interpretation of these structural estimates that's coming out of this paper. Anyway, so in the exercise we'll do it and try to see if we can estimate it. And this is actually just the Python output that we just I just pasted into the slide deck just for you to see if you can get the same result as a check when you do the exercises. Okay, so yeah, let's just check if they're the same. 9.8843. Well, that was lucky. Huh? So the code seemed to work. Okay, so there's some issues here about allocation, which is kind of general to discrete choice models. We can identify only the parameters relative to the scale of the error term. So let's call that sigma here. So what we identify is RC divided by sigma, and the same thing with the cost function relative to this parameter sigma. Okay, so if you do that math, you get something like theta 1 divided by sigma. That's what your cost function would be scaled by. Okay, so it's really the problem here, if you only have discrete choice data, is you need to make some normalization, and you don't really know from discrete choices and the state variables what the overall scale of the cost function are in terms of dollars. So, you know, theta is not identified for mileage and replacement data, period. Okay, that's a well-known thing from discrete choice models, like, you know, your undergraduate statistics you would have, or econometrics, you would have seen that. So how do you deal with that? I mean, you could actually go out and calibrate the model using, or bring in more data. So say using replacement cost data and the structural estimates together, we can obtain a scaled estimate. And John is doing that in his paper, and I'm going to review that example here. Okay, and scale estimates with observed average replacement cost. So he asked Hirosaka, how much does it actually cost to replace an engine? Okay. So with that estimate, he can actually figure out what the scale of the cost function is in dollar values. Let's try to take a look at that. So here's some data. It's a table for the paper, and you can see from, say, the replacement costs are higher for group 1, 2, 3. This group here, the total cost of replacement, although the engine replacement for this group occurs 57 miles earlier and 50 months earlier compared to group number 4. Well, you can see that here, but that's in the paper. Okay, so you know, why would you have higher replacement cost and then replace more frequent? Maybe it's because it's different types of buses. Okay. So presumably the operating and maintenance costs for those buses are increasing much faster. Okay, or you could have that, and if you could get data on these maintenance costs, you could have another test. We can test whether this hypothesis actually holds. Anyway, so in order to identify the scale of the cost function, we could use these data, these replacement cost data, and the structural estimates from, say, table 9. So those parameter estimates we just looked at. They're by the way here. This is for the fixed point dimension of 90, and then what we have is the actual replacement cost, those from this slide down here, and then we have the estimate, which is RC divided by sigma. Okay, now if we divide those two with each other, well, you would have the scale of the error term identified in some sense. Okay? So we can do that. So we got the replacement cost of $9,500, and then you got the parameter estimates 11.32 on the next slide. This is this number here, our scaled estimate of the replacement cost. Now dividing these two with each other, we get we get some number. Okay, and we can do the same thing for bus number 4. Okay, now with those estimates in mind of these, we can rescale the cost function, and then it's essentially just inserting into this cost function where you have the scaled estimate here, and our value for sigma, the variance or the scale parameter of these structural errors. Put that in, and then you just do the math, and then you get $3.9 times x, which is mileage bends. Okay. And whereas for bus group number 4, where the replacement costs were lower, you have 1.7 times x, $1.7 times x. Okay. And it actually makes a little bit of sense, right? Because this is a more homogeneous group of buses compared to this one, so it makes sense that the epsilons have a lower variance in that group. Okay, so to conclude, a bus of mileage 300,000. Okay, now we divide with 5,000 because it's a bin width, the length of each bin. There were like 450,000 miles in the state space, divided into 90 bins. That's 5,000 miles per bin. So x is equal to this number here. Okay, and then if you calculate the average, the difference between the cost functions between the two bus types, and multiply with x, then you get that on average it's $132 more expensive to operate a bus per month if it's of type 1, 2, 3. Okay, So you can make calculations like that if you have this outside information on what the costs are actually were in mileage in terms of dollars. And by the way, these dollars are $1,987. So maybe prices have changed a little bit since then. Take that into account. But you see the point. Okay, so otherwise it'll be very cheap to replace bus engines and drive them. Okay, so I mean we pretty much already talked a little bit about many of these things, like and maybe I'm repeating myself a little bit here, but why a dynamic model? Well, we talked about how the replacement cost would be downward biased if you were not taking into account the dynamics, because you would have to, by the principle of revealed preference, if you have to rationalize why you're making all those replacements, well, then you need to have lower replacement cost if you are assuming that he's not even thinking about how that helps him in the future. Okay, so, but generally, I mean, this is a issue which is clear in this model. But generally, the model, our estimates of replacement cost are any parameters that indexes these dynamic investments, which is be biased. Okay, parameters are the parameters of the cost function would be biased too, and so RC is upward biased, and theta 1 is downward biased. Okay, so it'd be biased for two reasons. Parameter estimates are biased, and the static model is just not correct. Okay, and it's not clear that, even though these biases by 1 and 2 might actually partly compensate each other, it's not likely that they just coincide and compensate each other in a way so that we just get the excellent correct predictions. So the short answer is dynamics are really actually quite important, and trying to identify what the discount factor is also important. And here we have an issue because the discount factor is not really very well identified. In fact, it's not identified if you have not put enough restrictions on the utility function. There's a paper very cool paper by Oystein Dalyard and Job Abring that is in QE, quantitative economics, that is dealing exactly with this, and they are then using exclusive restrictions on to identify that parameter. So they need variables that is affecting only future utility but not current utility, or vice versa, to identify the discount factor. Making a lot of sense, of course. Okay. Okay. So final thing I want to talk about is this bottom-up approach, or how you find the demand function for engines as a function of the price, the replacement cost. Okay, but before we go there, we'll start about the equilibrium mileage distribution and the demand for engines. Okay, now let pi be the long-run stationary distribution of the control process D and T. Okay, now I sorry for this notation. It should have been D, the discrete choice, and then the mileage. Okay, the replacement and mileage. Okay. Now, what do I mean by the long-run stationary distribution? I mean that if you take the controlled Markov transition matrix implied by the model, now this depends on both the choice probabilities and the transition probabilities of the conditional transition probabilities of the state variable process. If you take that Markov transition process, of the Markov process, it actually has an ergodic distribution. So it's like, you multiply it to you let it work on some distribution again and again and again and again, and then eventually in the long run it has converged to a stationary distribution. Okay, and that's the stationary distribution that we're looking for. How can you solve for that? Well, that's actually a fixed point of this functional equation. Okay, so here is really the this is really the transition matrix, right? This is the transition matrix or the transition probabilities for the mileage process, conditional on the choice, okay, and conditional on today's state, okay, and then that's multiplied with a probability of replacement, okay. Now, so if you want to find the fixed point on that equation, well, you see that the distribution is appearing on both sides, okay, and this is is possible to solve, right, by successive approximations. Okay, so clearly the equilibrium distribution applies an implicit function of the structural parameters, which we'll also emphasize. Okay, so now the equilibrium distribution will change as you change say the replacement cost. Okay. Now, so we have now our method to calculate the equilibrium distribution, and we can now also see how this equilibrium distribution changes as we changes the replacement cost or other parameters in the model. Okay. And then given this distribution, we can also get this formula or simple formula for calculating the annual equilibrium demand. Essentially, you know, that's 12 months, and then we are integrating over the state space to get the average the average monthly demand for engines, or the average monthly mileage, and then aggregate up by multiplying with 12. Okay, so now we have a formula for the equilibrium demand for engines, and say, since this depends on RC, well, then we can just vary RC, the replacement cost, and see how that demand is varying with the replacement cost. Okay, we have pictures. Okay, so here's the equilibrium distribution of mileage, the probability of the probability density for each of the grid point, for each of the values of mileage conditional on replacing, and then the distribution the conditional on keeping, and then the distribution conditional on replacement. Okay, so you see here really that it's the older buses that are replaced, and the newer ones there's more mass for buses that has essentially just been replaced. They are down here. Okay. So that was really pi, and then the equilibrium distribution of bus mileage coming out of model element, by the way. And then you have the demand, which was a function of the replacement cost. And then you can vary how the demand, or you can vary the replacement cost, and then resolve the model, and then recalculate the demand, vary the replacement cost, and then you get a demand curve. And you see it's downward sloping. It's essentially the higher the demand, or the higher the price, the higher the replacement cost, the lower the demand for replacing the engine is. And so this is this bottom-up approach which is based on a micro-aggregation of the outcomes of the model. Okay. So, final thing, why not just estimate that demand function, demand system, regress engine replacement on replacement cost? Why not just do the usual regression? We can easily fit this with some, a bunch of polynomials, and we just, throw in essentially expected annual engine replacements on the left-hand side, and then vary what the replacement cost would be. See, the problem is really the lack of variation in the data, the lack of variation in replacement cost. Data would be totally clustered around the intersection of the demand curves for beta equals 0 and beta equals 0.99 in this area. Okay. So here you got the cost of replacing bus engines here. You see, if you have very little variation in what the replacement costs are, well, the data is going to just be looking in this area. You're not going to have any observations up here or down here, and making experiments where you 10 double the price of the costs is expensive for the providers of that machinery that's sold to Harris Sucker. Okay, so this is a limitation of the data-driven approach without a model. We need to learn about the incentives, the structural parameters in a more indirect way, predict what the implied demand would be from that theory model. So demand also depends on how operating cost varies with mileage. Okay, and and so that's a problem too. And we really need the exogenous variation in replacement costs. It doesn't vary with operating costs at the same time. If that was the case too, you would need to control for that as well. And now you have two potentially endogenous variables that are prices, and you need instruments and so on. And even if we had exogenous variation, this does not help us to understand the underlying mechanisms of the engine replacement model and how the demand for engine is varying with the price of the assets that is replaced or renewed. Or if you think of, say, other cases with discrete choices like career choice, how the price of going to college, say a tuition fee, is pushing people into different occupations, into out of school or and into the military and so on. We can't really learn that from estimating demand systems or equations. We need to understand the underlying mechanisms and institutions and program the whole thing up. Okay, so I'm going to conclude now with what I will say is some of the very attractive features of the structural approach, and then I'll mention some of the less attractive features in just a second. Okay, so first of all, the structural parameters has very transparent interpretation within the economic framework. We know what RC is, right? It's a replacement cost. We know what theta 1 is. It's a slope of the cost function. Okay, these economic meanings are easy to understand. Okay, and then also evaluation of new policy proposals can be done by counterfactual simulations. This is something that's usually really a weakness of the more experimentalistic treatment type reduced form approach is the external validity of the statement you're making. You're really oftentimes narrowly focusing on identifying some treatment effect that is really, really local. So then someone comes and you've estimated these treatment effects of some program, but then someone comes and says, why don't we make another program? Well, we don't have any instruments, okay? So we can't really say anything about that. And then here within this framework, different economic theories can be attested against each other, like what it was done here, myopic relative to forward-looking behavior, or whether the buses were replaced differently and so on. Or you can have various versions of the model. So it's because the theory is so transparent, it's so easy to test economic theory. Economic assumptions are also very transparent and very explicit, and I mean, this is a matter of taste. I would say it's more explicit for me as an economist compared to making statistical assumptions like unconfoundedness, or whether X and Y are uncorrelated can be hard to justify, right? And it often, many of the discussions about treatment papers often end up in all sorts of anecdotes and stories about why this variable should be correlated with this or not. Okay, this is not one of the cases here. We're very explicit about what the economic assumptions are, and we can think about them within the lens of economics, economic theory. So I find that very appealing. Some people find it very scary that you can really see what those economic assumptions are, and say that this makes the approach extremely simplistic and full of hard assumptions. But there's a thin line there in terms of how you feel about how you should do empirical work. And this is not to bash really the how to do that, saying that estimating regression discontinuity designs or using state-of-the-art methods from the treatment shelf is not a good idea. I think these things really complement each other in a very good way. Anyway, so some of the less attractive features are obviously we impose more structure and make more assumptions, and we are and although being very explicit about those assumptions, sometimes we are forced to make assumptions simply just because it makes a model tractable and it makes it possible for us to compute. Okay, so well, my answer to that is, well, then we just need to work harder and come up with more realistic assumptions and more elegant models that are not so hard to reject, and I think you learn a lot of the economics in that process. And then you can say truly structural parameters may not even exist, like policy invariant. That's what I think of a structural definition of a structural parameter. So in this case, I would say that if the policy is say what could the policy be here? If the policy is we want to do a college subsidy in the presence in the career decision of young men model, and see how that affects enrollment into schooling and accumulation of human capital, well, then it cannot be that those parameters, the parameters that indexes the return to human capital is suddenly dependent on what that parameter is. Okay? In that sense, it's a structural parameter in the sense that it's policy invariant. Okay, so and this may not be possible to specify the model so that that's credibly true. Another thing here is the curse of dimensionality. You've seen that already, but we have a model here with one continuous state variable. If you have one model with two continuous state variables discretized into, say, 100 point, you have 10,000 combinations, and then with three state variables, it's not 10,000 combinations. It's I'm already out of, I'm running out of zeros pretty fast. It's increasing exponentially. Then there is the allocation problem. Here we have the issue that without any information about the cost or any exclusive restrictions that really moves the dynamic incentives, something that affects utility in the future but not now. You cannot identify the scale of utility. You cannot identify the you can't identify the discount factor. Okay, so sometimes it's just easier to go out and elicit time preferences by making experiments and so on. And then there's a problem of multiplicity and indeterminacy of equilibria. That's really a big issue in dynamic games, as we'll talk about later in the course, and making the model extremely demanding to solve. And then I would say it's hugely intellectually very demanding and a huge amount of work to do structural econometrics. I mean, you have to do need to know about collecting data, need to know about institutions, you need to know theory, you need to know programming, numerical analysis. It's so many things that you need to combine in order to just write one structural paper. And many of the papers I've been writing on have been going on for like half a decade, so sometimes even more. And that can be a really huge impediment on your career if you're trying to reach a tenure clock. So in that respect, my best advice is really, write a couple of, IB papers on the side and, that you can try to publish fast, and then do with the fun stuff, structural econometrics in the longer run. Okay, so that's it for part 2, and I'm